Hi, so it's the first day of the new term and the start of 2025, and whilst we're planning ahead for the next year, I decided to record a little review of what we've been doing over the past year. I'm not going to be going into details, but hopefully this will give you an overview of the type of robot learning research that we do in our lab and the direction we're heading in. So first up, at ICRA we presented Dream to Real. This is a method for object rearrangement. With Dream to Real, we found that if we can get a robot to build up a 3D nerf of a scene, it can then imagine what the objects would look like if they were placed elsewhere in the scene by rendering images of those imagined placements. We can then use a vision language model to evaluate the quality of each placement based on a language command for that rearrangement task. So in these two examples, you're seeing the scores for all these imagined placements as a heat map, and the robot is then choosing the best one to move the object to. We also presented Dinoot at ICRA. So take a look at these images on the top that were captured during a demonstration of a task. We found that by using Dino features, we can then find key point matches across different instances of an object class. And then when we apply this within an imitation learning framework, this enables a robot to generalize a single demonstration to novel object instances by using these key point matches to align the image from the wrist-mounted camera with the most similar image from the demonstrations. But what about if the robot is using an object such as a tool, but that object is grasped differently to how it was grasped during the demonstration? At IROS, we presented a method which enables a robot to adapt a skill to a novel grasp pose without having to provide any additional demonstrations. This is fully self-supervised. All we need to do is provide a single demonstration of the task, and the robot uses a self-supervised approach to autonomously learn how to adapt the trajectory for any novel grasp pose it may later encounter. And following on with the theme of self-supervised learning, at Coral we presented Miles, where we figured out how to get robots to learn very precise tasks from just a single demonstration. As you can see here, Miles works by building up a self-supervised dataset, which is then fused with the single demonstration to learn a closed-loop end-to-end policy for a task, but only requiring that one demonstration. And these videos here show Miles being deployed for a range of everyday tasks, including novel distractor objects. And in the corner of each video, you can see the wrist-mounted camera which the robot is observing. Language has also been a very hot topic in robot learning over the last year, and we've continued exploring this ourselves. So in our RA Letters paper, we studied whether large language models possess an internal ability to reason about 3D robot trajectories given object bounding boxes, but without access to any demonstrations or external trajectory optimizers. We were surprised at the strong performance here, with some tasks being very easy to solve using a language model's inherent understanding of 3D data, but other tasks requiring high precision were much more challenging. Another opportunity we found with large language models is their ability to perform in-context learning, and so we decided to study if this was also true in robotics. At RSS, we presented key point action tokens, where we represent both observations and actions as 3D key points in the form of text, which means that both the inputs and outputs of a robot's policy can now be understood by a language model. And in this video, we can see what this looks like during deployment. So after providing a few demonstrations of a task, the language model can then use these demonstrations as context in order to then predict the actions for a new example of that task. So in that Key Point Action Tokens project, we provided kinesthetic demonstrations. But what if we had access to a large data set of humans performing tasks with their own hands? In R+X, which stands for Retrieval plus Execution, we developed a method to query such a dataset using a vision language model to retrieve the most relevant human demonstrations for a task described by language. And by extracting the human hand trajectories in those retrieved videos, we can then use Key Point Action Tokens to perform in-context imitation learning, enabling a robot to execute language-conditioned tasks without requiring any robot demonstrations at all. And finally, in our most recent work that continues with our interests with in-context learning, we wanted to see whether we could train our own neural network that is designed specifically for in-context imitation learning in robotics without just using an off-the-shelf language model. So this graph neural network here, we design conditions one or more demonstrations, and we can then predict actions for a new example of that task using a learned diffusion process. And what's really exciting about this is that the network can be trained using only simulated pseudo demonstrations, making the approach highly scalable. And these videos now show our method, instant policy, being deployed to learn novel tasks instantly from just a single demonstration each. As you can see here, these are closed loop policies which react in real time to disturbances in the scene. So given these strong results, we're really excited now about the future of in-context learning as a strong competitor to the standard behavioral cloning paradigm. So thanks very much for watching, and I hope that helped to give you a quick overview of what we've been up to over the past year and the direction we are heading in. Stay tuned for more and have a great 2025.